Okay, so this problem is pretty intense, so it's going to take a little while. Here we have water is leaking out of an inverted conical tank at a rate of 6,000 cubic centimeters per minute. At the same time that water is being pumped at a constant rate. Pumped in at a constant rate. The tank has height 700 centimeters and the diameter at the top is 600 centimeters. If the water level is rising at a rate of 29 centimeters per minute when the height of the water is 150 centimeters, find the rate at which the water is being pumped into the tank in cubic centimeters per minute. Okay, so that's a lot of information. Let's draw a picture first to try to see what's going on. We have a conical tank, and this conical tank has a constant radius. So the radius is, it says the diameter is 600 centimeters, so that means the radius is 300 centimeters. And the height of this cone is also fixed. It's going to be 700 centimeters. Okay, so these numbers I can put in right away because those are constant. Those are never going to change. The radius of the cone is always 300. And let me call this capital R. Okay, so the radius is 300 and the height is going to be 700. Okay. Now it says that water is being pumped in. So water is being pumped in. So let's say you have a little pipe here and water is flowing inside, but then also there's a hole down here and the water is also leaking. So it says that it's leaking out of an inverted conical tank at a rate of 6,000 cubic centimeters per minute. At the same time that water is being pumped in at a constant rate. So there's water being pumped in, there's water being pumped out, and so the volume of the water inside depends on how much is being pumped in and how much is being leaking out of the bottom of the cone. Okay, so the question that it's asking us is find the rate at which the water is being pumped into the tank. Okay, so this is a little bit tricky, but let's explore the idea that I just mentioned. Is that the rate at which the volume of water inside of the tank is changing. So let's say we have here water level. The rate at which the volume of water is changing is the difference between the rate at which the water is being pumped in and the rate at which the water is leaking out. So what this means is that the derivative of the volume with respect to time is equal to the rate in minus the rate out. And this makes sense, right? Because if you think about it, well, the volume of water is changing. The rate at which it goes in, that's going to be positive because it increases the volume. But then the water is also leaking out, so you have to subtract that water out. And notice that, well, we know that the rate at which it's going out is, it's telling us right here, it's 6,000 cubic centimeters. And the rate at which it's going in, this is what we're looking for. We're looking for the rate at which it's coming in at a particular point in time. And that particular point in time, that when, is given right here. It's saying that if the water level is rising at a rate of 29 centimeters per minute, key word here, when the height of the water is 150 centimeters, find the rate. So this is the point in time that we're looking for. So here at 29 centimeters per minute, this is the rate of the water level. So let's call the water level, let's call that H, because it's basically the height of the water. So that means that this guy, 29 centimeters per minute, this would be dH over dt. Okay, so that means that we're looking for the rate in when dH over dt is equal to 29, and also when the height of the water is 150 centimeters, so when H is equal to 150. Okay, so that's good. Now let's finish labeling our picture over here. What we have then is that if we draw a little line here, so this is the water level right here. This is H. And here, this is, I'm going to call little r, I'm going to call that the radius. See how we have another, if you look at this, this is another smaller cone inside, made up by the water, the body of water inside of the cone. So here we have little h, which is the water level, and then little r is the radius of the cone created by the body of water inside of the cone. Okay, so now that we have all of that sorted, well, we can come up with our formula. Our formula that relates all of our information is going to be the formula for the volume of the cone. And the volume of a cone is equal to 1/3 pi r squared times h. Okay, so here we have a little situation. Notice that we have r and h. So if we get the derivative of both sides, we have the radius and the height. Those are both functions of time, meaning that as time passes, both the height and the radius, the little radius inside of here, those are both going to change. That means we have to use the product rule. But there's a little way around it using a little trick, and the little trick involves noticing that inside of here, if you look at this as one triangle formed by cutting the cone in half, you have one big triangle, you have one little triangle. These are similar triangles. So you can set up a proportion here. You can say that H over R is equal to 700 over 300. Okay, so the good thing about this is that, well, now that you have it like this, since notice that the information that we have is all on h. We have the derivative of h with respect to time, and we have h at a particular point in time. So we could use these to find the radius at a particular point in time, but it's easier to rewrite the volume formula in terms of just the height, because that way we just plug in the information that we already have. Okay, so using this, we know that if we solve for r here, we would get that r is equal to 3h over 7. And if we then plug that into our formula for the volume, we would get 1/3 pi 3h over 7 squared times h. Okay, so one more simplifying step. I would get, if I square the 3, I would get 9, and then it simplifies with this 3. I would get 3 pi on top over 49 by squaring the 7 times h cubed. Because h, this would be h squared times this h right here would give me h cubed. Okay, now that I have this, now I can get the derivative of both sides with respect to time. Okay, and so here on the left I have the derivative of the volume with respect to time is equal to 3 pi over 49. That's just a constant, so I'm just going to leave this out of the entire thing. That the derivative of h cubed, well, this is, I have to use the chain rule, so it would be 3h squared times the derivative of h with respect to time. Okay, and now I look at this and I go, okay, well, I know what this is. dv over dt, this is what I have right here. This is the rate in minus the rate out. Rate in is the one that I'm looking for. So let me call this guy rate in. I'm going to call it RI. Rate in minus 6,000. Okay. So that's that one. And then H, I have that. Well, that's just 150 centimeters, right? I have it right here. And then dH over dt, this is 29 I have right there. Okay. So if I plug all of that stuff in, I'm going to get the rate in minus 6,000 is equal to, I need to multiply all this stuff out, so I would get 5,872,500 pi over 49. And so the rate in is equal to this whole thing, if I approximate it, I would get 3,76510, and then I need to add the 6,000 on both sides. Add the 6,000 on both sides, and so that means I would get, this is equal to 382,510 approximately. And this is cubic centimeters per minute. And that's it. That's the rate at which the water is coming in. And it's coming out at 6,000 cubic centimeters per minute.